All right. Aloha, everyone. Welcome to Wednesday. 2 weeks from today, we will be half an hour into our final. Everybody note the difference in time, okay? Our final 2 weeks from today is at 10:30 in this classroom. 10:30? Yes. I have a final from 8 to 10 for my OChem class also. So if you have any last minute questions, I will not be in my office. I'll be in here. Probably be here a few minutes early, ready to start. But 2 weeks from today and 2 hours, you will be completely done with this class forever. Unless you don't do well. And I'm teaching it again in the fall, and you can do it again in the fall and kill it this second time. Okay? Or you can just kill it this time and do good. There was an exam that was due today about 2 minutes ago. You had to submit it via Canvas. Hopefully everybody did okay on that. You all talk to your friends about it, get all the answers squared away. Yeah? No? Good. You weren't supposed to. Okay. So last class, we talked about spontaneity. Who wants to summarize it in 39 words or less? Jack, thank you for volunteering. Go ahead. Explain spontaneity to us.
Lowering in energy.
Pretty good. That was pretty good. That was less than 39 words. Jackson, what do you think? You agree? Exactly. Perfect. Okay. So, I mean, who can summarize how we know if a reaction is spontaneous? Lucian? Like in the hair? I want to know. Okay, you guys are talking about what a spontaneous reaction is. I'm asking if I give you a reaction with a exothermic or endothermicity, how can you tell if it's spontaneous or not? We should be able to do that. Sometimes it's always spontaneous, sometimes it's never spontaneous. And then there's a couple situations that are spontaneous above a temperature and not below, or vice versa. So, Jackson, any thoughts on this? Very excellent point. Okay. So what we're gonna see, an exothermic process. Okay, so one step behind that. Okay. What Jackson was saying is this equation right here. Why is it not on? HDMI. No wonder. Thank you. Okay. So the reaction is the delta S of the universe equals the delta S of the system plus the delta S of the surroundings. So we're going to focus on the delta S of the system. That's the actual reaction that's happening. Does anybody remember how to determine just by looking at the reactions if the delta S of the system is positive or negative? Robert, any thoughts on this?
Exothermic is positive and endothermic is negative.
That is for the surroundings, though.
That's for surrounding.
Yeah. So someone came into office hours today and we went over everything we're going over today and from last class. And I came up with this little cheat sheet. Okay. So overall, the delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. Okay. That's a formula that you just need to know. Okay. The second law of thermodynamics states that all spontaneous reactions must have a positive entropy. Delta S of the universe is positive. Okay. So these are like what we're saying in stone. A reaction cannot be spontaneous, and that was great definitions of what a spontaneous reaction was. But a spontaneous reaction has to have a positive delta S of the universe. Okay. So what I was asking is, if we can figure out the sign for the delta S of the system, then that gives us this. If we can figure out the sign for the delta S of the surroundings, then that will give us this. Sometimes if they're both positive, the universe will always be positive. That reaction will always be spontaneous. If they are both negative, that will always make the delta S of the universe always negative, and that would make that reaction always non-spontaneous. But then we have the situations where one's positive and one's negative. And for those reactions, there's usually going to be a cutoff. So if one's more positive than the negative, then it is, or vice versa. So one thing that I showed last time, but we didn't really talk about, was we can actually quantify the delta S of the surroundings by going the negative delta H of the system over the temperature in Kelvin. Okay. Since we're putting the temperature in Kelvin, do we all agree that we can never have a negative temperature if we're putting it in Kelvin scale, right? What that tells us is that whatever the delta H of the, what does that say? System is, that's kind of, I don't know if it's supposed to say that. So the delta S of the surroundings will always be the opposite of what the delta H of the system is. The delta H of the system is whether it's endothermic or exothermic. So I wrote over here, when delta H is negative, is that an exothermic or endothermic reaction, Cade? It's written right next to it. When we have an exothermic reaction, that means that the delta H of the reaction is negative. If you forget this, remember it. If you have a hard time remembering things, write it on a note sheet. Are you allowed a note sheet for the final? Sure. Okay, you can have one sheet of notes for the final. Okay, you can write whatever you want on there. If you forget to write on a note sheet, how can you remember whether delta H is negative, is exothermic? What does exothermic mean? It releases heat to surroundings. Think about your bank account. When does your bank account become negative, Yasmin? When you release money to the rest of the world, or when you absorb money from the rest of the world? Which time does your bank account go more negative? When you release money to the world, when you spend money. Everybody understand that? When does your bank account get more positive, Nana? When you get money from people or you absorb, whether it's be getting paid, getting money from your parents, getting paid back from your friends for Venmo and things like that, right? So the take-home message is in an exothermic reaction when delta H is negative, that means the delta S of the surroundings is going to be positive. Delta S of the surroundings is always going to be the opposite sign of the delta H of the reaction. We can quantify it. When I say quantify, that means actually make the numbers, like figure it out. We need to know the numbers when it's a situation where we have a plus and a minus. If they're both pluses, we don't give a crap about how positive it is. We always know it's going to be positive. Or if they're both negative, we'll know that they're both negative. We do have to quantify it when we have one positive and one negative, okay? So we'll do all these things. But this basically summarizes, in an endothermic reaction, delta H is positive. That means it's absorbing heat from the surroundings. That means it's cooling down the everything else. If I'm taking heat from the surroundings, isn't the surroundings going to get colder? How does that affect our entropy, Ian? If it's getting colder, is there more entropy or less entropy? Everyone agree with that? When it gets colder, there's less entropy, right? When it's hotter, there's more entropy, right? If we are little gas particles and the temperature is the speed that we're moving, if it's really hot in here and we're sprinting around the room as fast as we can, would we agree that there's more possibilities of where we're all going to be than if we're moving at like one step every minute because it's cold and we're going real slow? Wouldn't we have a lot more likely chance of like pinning down where everyone is at a cold than if they're running around all crazy? Yes? No? Thoughts? Yes. Okay. Everyone's slow. So there's going to be less randomness for the people moving slow, correct? So that's going to help us determine the delta S of the surroundings. That figures out one half of this situation. To determine the sign of the entropy change for the system, this is what I was asking you, Robert. So how do you think we can figure that out? So that's one way, but we usually don't have the entropy of the universe. So the way that I asked you to remember it last time is if we have more moles of reactants than products, is that getting more ordered or less ordered? What do we think, Nate? You have more reactants, 7 reactants becoming 4 products. Is that getting more chaotic or more organized? So is that a positive entropy or a negative entropy? Entropy is a measure of disorder or chaoticness. Then that would be a negative. So when you have more moles of reactants than making less moles of products, that is a negative delta S system. Does that make sense? Okay. Conversely, if you have less moles of product, 3 reactants making 8 products, and any of these numbers could be like 3 to 4, 3 to 5, 3 to 9, any smaller getting bigger. That is getting more or less organized. Carissa, 3 reactants making 8 products. Is that getting more or less organized? 3 things making 8. Less organized or more chaotic, right? So entropy is always confusing because when we're measuring something getting more disorganized, that's the positiveness, right? Getting more organized is negative. You just have to get this straight in your head. I know we only learned about it like kind of a lot on Monday. So you have to think about this and you have to practice the stuff. So we get 3 to make 8. That's going to be a positive entropy. It's getting more disordered, right? So that will be, so now we get this. If we know one's positive and the other's positive, this is always positive. Boom. If the delta S of the universe is positive, the reaction is spontaneous. If the delta S of the universe is negative, then the reaction is non-spontaneous. Do we understand that? Okay. So when we're just finding if it's positive or negative, there's 4 possibilities, right? We can either have positive, positive, or negative, negative, and those will always have a set answer, right? But we could also have positive, negative, which will be above one temperature it is, below it is another. Is freezing of water like that? Does it always freeze? No, it only freezes below a certain temperature. It's also like saying, does water always melt? No, it only melts if it's hotter than a certain temperature. If it's negative 20 degrees, ice is not going to melt into liquid water, right? So that would be a situation where you have either positive, negative, or negative, positive. So those are the 4 situations we're going to look at. So let's do that example we did last time. Okay, so if we have to quantify, meaning if we have to actually find the value of the delta S of the surroundings. So I said that thing that I just said was the note sheet said when delta H is negative, delta S surroundings always positive. When delta H is positive, delta S surroundings always negative. So delta S of surrounding is always opposite. Notice that if we need to know more than whether it's just positive or negative, if we want to know a value, we would actually take the value of the delta H of the system and divide it by the Kelvin temperature to get the delta S of the surroundings quantity or number in the case where it's a plus and a minus, and we have to know if the plus outweighs the minus or the minus outweighs the plus. Does that make sense? So that's going to be the situation we're going to do over here. Okay. So this question's asking, let's look at the combustion of propane gas. You take 1 mole of propane plus 5 moles of oxygen, and that produces 3 moles of carbon dioxide and 4 moles of water. Okay. So is those numbers going to help us with A, calculating the entropy of the surroundings, or B, calculating the entropy change of the system? What do we think, Donatella? I know it looked like you were getting tired, so I figured I would jump you into okay. So I'm showing you the number of moles on the reactants and products. Is that going to help us determine the surroundings or the system? Guess again. Very good. The system, right? Because the system is the actual things that react. The surroundings are determined by what, Robert? That's what you were saying the first time?
They are determined by the reaction is exothermic.
Very good. So if the reaction is exothermic, it releases heat to the surroundings. It heats up the surroundings. Entropy is increasing for the surroundings in an exothermic reaction. Everybody agree with that? If the reaction is endothermic, it pulls heat from the surroundings. It cools down the surroundings. Therefore, the entropy change of the surroundings would be negative in that case. Everybody see that? So let's see. Janessa, this reaction has a delta H, which is negative. Is that exothermic or endothermic? Your bank account is getting negative. Are you spending money out or are you pulling money in? You're spending it out. So if we're talking about heat, you're spending heat out. Is that going to heat up the surrounding or cool down the surrounding? If you're emitting heat, you're emitting heat. If you want to cool down, you're going to go next to a heater. Oh, this heater is going to emit heat. Let me go sit by it to cool down. What do you do when you sit by a heater? You get hotter, right? So it's going to warm up the surroundings, right? When something releases heat, it warms up the surroundings, thereby. So, Ida, what is going to be the entropy change for the surroundings, positive or negative? Everyone agree with that? The surroundings are getting hotter. Is the entropy of the surroundings increasing or decreasing? Increasing. It is going to be positive. We could actually quantify it, okay? So the way we would quantify it is we would take that negative 2044, but the formula is negative delta H of the reaction over the T. So this told us that the reaction was at 25 degrees. We convert that into 298 Kelvin to get that. It is positive. It actually quantifies it. Sometimes it'll matter if it's the actual value. If both things are positive in this case, we don't really even have to worry about that, okay? So you always want to check if both signs are the same direction. So Nana, we got that A. So the equation we're trying to find is delta S of the universe. We want to find if it's positive or negative, and we do that by doing delta S system plus delta S surroundings. So what did A just tell us? Surroundings or system? Nope. Guess again. Very good. And was it positive or negative? Very good. You see that positive sign right there? So this is a positive value. Everybody good with that? Okay. Now, the sign, let's determine the sign of the entropy change for the system, Riley. Is the system positive or negative? I'm going to give you a hint. These numbers are going to be important. So how many reactants do we have? And how many products do we have? So if you have 6 things becoming 7 things, is it getting more organized or less organized? Less organized, and so more disordered. Entropy is a measure of disorder, so would that be a positive entropy or a negative entropy? It's getting more disordered, so it's getting more entropically favored. So is that positive? I'm trying to push you to positive. Yes. Okay. That means that because it goes from 6 to 7, it's getting more disordered. Delta S is positive. And let's verify that. You see how it says 6 moles of gas makes 7 moles of gas? This is positive. Positive plus positive. What is this always going to be, Abby? If you have a positive plus a positive, it's always positive, right? So would we say that this reaction is, so that would give us a positive over here. Would we say that this reaction is spontaneous or non-spontaneous, Meredith? Everybody agree? Positive delta S universe means spontaneous reaction. So we have a positive plus a positive, therefore delta S universe is positive, and the reaction is spontaneous. Okay? Everybody got that? So just as an update for lab next week, I'm basically gonna make like a final exam, and that's what you're gonna do in lab next week, okay? So those of you who do my practice final exams do a lot better than the people who don't do the practice final exams. How do I know who does? Your scores. Maybe some of you could still do good if you don't do it. And maybe you could look at the practice final and not do good. But I promise you, when you don't look at the practice final, you're not going to do as good as if you do. So go to lab next week and work on that practice final exam. Okay? That's what you're doing in lab. My lab, we're checking out today. That way we can just come in and do the worksheet. Well, those of you who have lab this week, if you didn't check out, you'll check out next week and stuff like that. But that's the way lab's going to be next week, okay? So you don't need to do anything for like the lab that's on the schedule next week. You just need to show up and get the practice exam or figure out with your specific teacher what you're doing. But we will still meet and we will do it, but I'm going to just give you a practice exam, and that's going to be basically a good indication of what the final is going to be like, okay? Here's a little hint. It is not a take-home final, okay? You know why I gave you a take-home final? I was hoping you would boost your scores, okay? So I'm hoping I don't have to do much correcting. So I'm hoping you didn't cheat though, but you know, you should know I'm not a cheater checker. I'm not like the person who I send in here to take tests who watches you all with eagle eyes, right? So let's do another example, okay? Justin, you do part A? Calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees C. So you could quantify it using this equation, or you can just tell me if it's positive or negative. Is the delta, so A is finding the delta S of the surroundings. Delta S of the surroundings is basically equal to the opposite of delta H. So is the delta S of the surroundings negative or positive in this case, Justin? Everyone agree with that? Why? What type of reaction is this, Justin? Guess again. Endothermic, right? It's positive. So why is the delta S of the surroundings negative in this case? So it is negative in this case, right? Angelina, why is it negative? It's cooling down the surroundings. That is decreasing the entropy of it, okay? So that's the sign. For B, determine the sign of the entropy change for the system. What do you think, Ricardo? How do we figure this one out? There's not really a formula. Let me show you my little sheet of notes. To determine the sign of the entropy change for the delta S of the system, when you have more moles of reactants than products, it's negative. When you have less moles of reactants than products, it's positive. So let's go back to our question. Do we have more moles or less moles of products or of reactants? Of what? Product. So is it getting more organized or less organized? It's getting less organized. Does that calculate to a positive entropy or a negative entropy? You're getting more organized. Does your room automatically get more organized or less organized? So that is entropy. Entropy is positive. So always think about it. Does your room self-clean? What do you think? My room used to when I was younger, because my mom would go in and look at all my crap and be like, "Oh, I cleaned your room, but I also found this in your thing." I'm like, "What the heck are you looking for all my stuff?" But you know, it's the way it is. So, is it positive or negative, Ricardo? Everyone agree with that? 3 moles becoming 2 moles is positive entropy. Everyone agree? Thumbs up or thumbs down? Let me see. What do you think? It's getting more organized. That's entropically unfavorable. So it should be negative, right? So the first one was negative. We could plug in the values to get the actual value. But since we're not getting the actual value of part B, we just need to know if it's negative. We see that the second part is negative. Everybody's comfortable with that. So Jessica, is this reaction spontaneous or non-spontaneous? Correct. Why? So since the delta S of the universe is negative, that means the reaction will not be spontaneous. Everybody comfortable with this? Yes? No? You think this slide right here is important? That is not on the notes. I just put that in there today. Okay, so let me save these notes. And I probably will not, it probably won't go into effect. You might want to ask Carissa for this piece of paper I gave her. She's going to charge $1 a piece, or you could write down everything on there. Everybody got their picture? Okay, good. Let's do a quick conceptual check. Do biological systems contradict the second law of thermodynamics? Anyone remember the second law of thermodynamics? What is it? Valerie? I mean, the second law of thermodynamics was the delta S of the universe is positive for all spontaneous things. Okay, so what we're trying to see is, does the delta S of the universe positive for all spontaneous things? So by taking energy from our surroundings and synthesizing large complex biomolecules, plants and animals tend to concentrate energy, not disperse it. So usually things want to spread out their energy, right? That's why like a concentrated fossil fuel wants to burn and spread out into like way more disorder. But like as a living system, we take a bunch of amino acids, a bunch of sugars, and we make them into these super unbelievably complex things. Is that delta S of the system going to be positive or negative? What do we think? Negative, right? So does it contradict it? Yes or no? Any thoughts, Ian? Does it contradict it? Yes or no? No, it doesn't. How could it not contradict it? Loit? Jackson? Very good. So if it's going to happen, if the delta S of the system is negative, but it's spontaneously happening, it must mean that the delta S of the surroundings are getting more. So the answer says biological systems do not violate the second law. The key to understanding this is realizing entropy changes in the system can be negative as long as the entropy change of the universe is overall positive. And the only way for that to happen is exactly the biological systems decrease their own entropy, but only at the expense of making the entropy of the surroundings much more disordered, right? So us as humans, we make things complex, but don't we just tear up everything else in the world? Do we chop down trees? Do we exhale heat and spread warmth everywhere and joy and love? Maybe not in chemistry class, but every other time, right? So that's how we do that, okay? Excellent. Let's move on to the next section. Gibbs free energy, okay? So let's talk about all the delta letters we've learned in thermochemistry so far. Give me one of them, Jack. Delta S was entropy. Give me another one, Jack. Delta H is entropy. Give me another one, Donatella. I know. Bailey, what's another one? Yep, so delta E, right? So have we had kind of our fair share of deltas? Let's learn another one, okay? We're going to learn something called Gibbs free energy, okay? Take a guess at what this one's going to be lettered. Whoa, good job. You see that G right there? You're a G, Donatella. So we're going to learn about delta G. What is delta G? I have no idea. Just kidding. Delta G is called Gibbs free energy and spontaneity, and it's basically a measure for, so Gibbs free energy is almost exactly the same as delta S of the universe, okay? It's going to tell us whether or not a reaction is spontaneous or not, okay? You're probably like, why did we just spend all this time figuring out if the delta S of the universe is spontaneous or not? just to have another variable and energy thing that's going to describe that. And the reason is people were able to quantify this delta G, make a bunch of tables with it, make a bunch of different like reactions with energies, and all of that stuff that you thought you didn't need from chapter 6 of 115A, when you did things like Hess's law, when you did the summation of the products minus the summation of the reactants. You remember all those ways we calculated delta H back in the day? We're going to do those exact same things, but we're going to do it in terms of delta G. So somebody, probably a lot of people, went to the extent of calculating the Gibbs free energy of all these different molecules, and it's going to help us determine if we want to do a reaction, if that reaction will be spontaneous or not. Does that make sense? I mean, it has to, because that's the way I'm going to explain it, okay? Like, you could like read about this on your own. You could probably watch like 15 Khan Academy videos to like get a better understanding for delta G, but it'll probably just confuse you more. Just understand that when I talk about delta G for the test, there's going to be some values that are associated with it. When you calculate delta G, if it is, so the thing that's going to be different is when we said that the delta S of the universe was positive, that referred to a spontaneous reaction, okay? When delta G is negative, that is going to refer to a spontaneous reaction. So basically, you could get confused if you don't get this right in your mind or write it onto your note card and stuff like that, okay? So what we're going to talk about now is how are we going to be able to calculate delta G for any given situation. So to summarize, Gibbs free energy is proportional to the negative of the delta S of the universe. And all that means is when a Gibbs free energy is negative or less than 0, it corresponds to a spontaneous process. So delta G is negative equals spontaneous. When delta G is positive, what does that have to mean? Amanda? Very good. That means the reaction is not spontaneous. Everybody see that? So easy enough, right? Let's do a little bit of review. Remember when we had to determine, so when we made an ice table, remember if we had to decide if it was plus X or minus X? How do we know which one it was, Merve? Yeah, that plus means gain and minus means loss. But how did you know which side was plusing and which side was negating? Negativing, subtracting. Very good, right? So we would, K was equilibrium. If it was not at equilibrium, we would solve for it in terms of Q, right? We'd plug our values in for whatever was not at equilibrium. If Q was less than K, it had to move to the right. If Q was greater than K, it had to move to the left. Do we remember that? Does that kind of light a fire in your memory? I was like at least more than a day ago, so I'm sure you don't remember it. But same kind of thing is going to happen with this. A process will be spontaneous when delta G is negative. So delta G will be negative when delta H is negative and delta S is positive. So basically, let's look at this formula, okay? This formula is going to be gold, okay? Delta G is equal to delta H minus T delta S. This equation is super important. Do you think you should write it down anywhere? Or do you think you should just be like, okay, I see it. I'll remember that for the next 2 weeks. You only need to know this stuff for 2 more weeks and 1 more hour. And really, if you finish that test in less than an hour and the test is written as a normal 50-minute test, you really could be done in 2 weeks from today. And you'll never have to think about general chemistry again, except for all the late work that many people submit at the very end. So, you could like, I get all these people who submit homework after the final and they get like partial credit for it. And I'm like, cool, I'm glad you did this all after the test when it doesn't help you. Why don't you do it a little bit before the test so that even if you're just copying down the answer key and submitting stuff, at least you're learning a little bit than just trying to get those partial credit at the very end, okay? So if you have a bunch of stuff missing, and if you have nothing missing, then don't worry about this talk, okay? But there's a crap load of people who still have zeros on homeworks and things like that. You should get those points. People do that after the final. That's the worst time to do it. It doesn't help you anymore. Do it before the final, and now it's actually beneficial. You're still getting less points, but you're getting free knowledge to help you for that final exam. Everybody understand that? So there's going to be 4 situations, okay? So to find delta G, so since the formula is delta G equals delta H minus T delta S, T is going to be the temperature in Kelvin. So what does that mean? That means it's always going to be positive. So does everyone agree that there's 4 different situations where that we can have? We can either have delta H is positive and delta H is negative, and delta S can be positive and positive, right? So if delta S is positive, delta H can be either positive or negative. That's 2 different situations. We could also have delta S being negative and this be positive or negative. So we can have positive, positive, negative, positive, positive, negative, negative, negative. There's 4 basic situations that can happen. Does that make sense? Let's look at each one of these situations individually, and that'll help us determine if a reaction is spontaneous. It's kind of exactly what we did with the delta S of the universe, but now the reason why the delta S of the universe is not always the best thing to look at is because we don't always know, we're not always able to quantify things. In this situation, we can, okay? So if delta H is negative, is that an exothermic reaction or an endothermic reaction? What do we think, Morgan? Delta H is negative is what? When your bank account gets negative, are you releasing money or absorbing money? Exothermic. You're releasing money, right? So this is an exothermic reaction with a positive entropy. A negative minus a positive will always give us what, Jessica? A negative minus a positive. No, it's not. -1 minus any number that's positive will always be negative. -1,000,000 minus any positive number will always be negative, right? So in this situation, it does not matter, right? A negative minus a positive is always negative. Does everybody agree with that? So in this situation, it's negative at all temperatures. Okay? So is this spontaneous or non-spontaneous, Kayla? So delta G is the opposite, right? Delta G tells us that when you have a negative delta G, it is a spontaneous reaction. Thinking about this in the terms that we talked about last class in the beginning of this class, didn't we say that negative delta H made the surroundings delta S positive? And we're saying delta S is positive. So now everything is positive. That gave us a delta S universe positive. So that's kind of why they contradict each other, right? So now in this case, it's negative at all temperatures. An example of this, 2 moles of gas becoming 3 moles of gas. It's a negative delta H. The entropy is positive. So we have a positive entropy. We have a negative enthalpy. So delta G is over here like that. Okay. So if the delta H is negative and delta S is positive, then the reaction is always going to have a negative delta G. Okay. What was that? Okay. If delta H is negative, so let's skip this one because that one's a little weird. I don't know why I have them in that order. In case 2, what if we have a positive delta H and a negative delta S? What will happen in this case, Angelina? If you have a positive minus a negative. So if you have money in your bank account and all the negative money you owe gets subtracted, Is your bank account always going to be positive in that case? You don't owe any money out. All the debt you have is gone. So that's like minusing a negative. So a positive minus a negative will always give us a positive. So in those two situations, we don't even have to like quantify. If we can just look at the signs, those two situations will always give us either always positive or always negative. Yes, Ella. So so let's say it's negative 7 kajillion, 7 times 10 to the 400 million. And let's say that this positive number was a small one, like 2. What is 2 minus negative crap load? Positive crap load, right? So no matter what, that sign will always be positive. And what does a positive thing tell us, Bailey? Positive delta G, spontaneous or not spontaneous? Not spontaneous, right? So delta G, Gibbs free energy, positive is bad. Okay. So now the other two situations, these are the ones that you two were thinking about, right? If it's negative minus a negative, at low temperatures, it's going to be negative, but at high temperatures, it's going to be positive. So this T factor, the temperature is really going to play a big role. And this kind of made sense, right? We were talking about this in terms of water freezing, right? We said water freezes at low temperatures, but it doesn't freeze at high temperatures. At low temperatures, it freezes because the exothermicity of it releases heat to the cold air, and that has an overall increase in the universe's surroundings. On hot days, that small amount of heat that's absorbed that releases doesn't affect because everything's already hot, right? So think of it like this. Would you rather turn on the heater in your car in the middle of summer, in the middle of the hottest day of the year? Would you turn your heater on, Meredith? But what about in the middle of winter at 2 in the morning when you get in your car? Do you think that's going to make a difference? So you turn on your heater when it's cold. You don't turn it on when it's hot. So that's what this is showing us, okay? So those are the situations. Let's do some problems to help us look at this. To summarize these things, notice that so this one is always spontaneous when it's negative delta H and positive delta S. This one is always non-spontaneous when we have positive and negative, the opposite. This one will be non-spontaneous only at, what does it say? So when delta G is greater than 0. So when they're both negative, that's going to happen at, so what is it? Delta G equals delta H minus T delta S. So if we have a negative and a negative, negative minus a negative, that's going to make that positive at high temperatures or low temperatures. What's the thought? Analia, what do you think? If it's a negative minus a negative, negative minus negative. So you think that temperature, high temperatures is going to make it that value more positive or more negative? Do we want this temper? So negative times negative is going to give us a positive, right? So the higher the temperature makes it more positive. This thing will happen at, it's spontaneous at low temperatures and non-spontaneous at high temperatures. You see that? The other situation is non-spontaneous at low temperatures because it's the opposite, positive minus a positive. Okay, if the temperature is low, we make the amount we subtract be small. So at high temperatures, we make this minus or positive, positive minus positive. At low temperatures, because we want it to be negative, right? So it's spontaneous at high temperatures because when this gets big, it makes this thing be negative. You will have to do some problems to figure that out, okay? So let's do a problem right here. Calculate the delta G at 25 degrees and determine whether the reaction is spontaneous. Okay. For part B, if the reaction is not spontaneous at 25 degrees, determine what temperature, if any, the reaction becomes spontaneous. That sounds hard, huh? Any thoughts on how we do this? So how do we do part A? How do we calculate if it is spontaneous or not? What do you think, Kayla? What are we going to use? Well, we're going to use this equation. So we need to find if delta is, so to find out if this reaction is spontaneous, it says calculate delta G. Here's delta G. That is not a negative. That's just a little dot, okay? So is this reaction, is delta H positive or negative over here? Positive. So it's a positive sign minus T, and delta S is positive. So a positive minus a positive. Is this always going to be positive, always negative, or it depends? Thoughts? Nate? Always positive, always negative, or it depends? Very good. So Lucian, let's quantify it, right? So we're going to take the temperature. It's 25, add 273 to get 298 Kelvin. We take the 95.7 kilojoules here, but why did I change it to 95.7 times 10 to the third joules? What am I doing? I just converted it into joules, okay? That way, when I times the enthalpy, which is in units of joules, times Kelvin, we do 298 Kelvin times 142.2 joules per Kelvin. Kelvin cancel, it gives us our answer in joule. We had to convert this delta H into joules, okay? So now that they're both in joules, we can add them up. We get a positive 53.3 joules. Is this a spontaneous or non-spontaneous reaction, Rebecca? Very good. Does everybody agree that it's not spontaneous? Yes? Why? Because it's a positive delta G, right? Now, how could we calculate? So if the reaction is not spontaneous at 25 degrees, so did we say it wasn't spontaneous at 25? Is that what we just said? How can we calculate the temperature where the reaction will become spontaneous? Huh? But I want to know the exact temperature. How could we do that? Let's think about that. You really like doing equations with the greater than sign? So what could we do? So what is going to be the situation where it flips, Jackson? So are we saying that it's not spontaneous right now? Yes. Well, no, let's just talk about delta G. Is it not spontaneous? We agreed on that, right? Because why? Okay, so when will it become spontaneous? So instead of using a plus or minus, what do you think we could plug in for delta G to figure out that flip from positive to negative? Does anybody know a value where a positive value becomes negative? Vase. Does everyone agree with 0? Is that the temperature or is that the value where it's going to flip from positive to negative? So all you have to do is plug in 0 into this equation, plug in all of our stuff, leave T as the variable now, solve for T, we get 673 Kelvin. Above 400 degrees Celsius is when this will become spontaneous. Everybody see that? Is that amazing? Now you can do a lot of your homework. You can't do it all yet, but you can do a lot of it. When's the homework due? I'm going to make it due next week at the end of the week at the minimum, okay? We still have one chapter left, so